Hi, everyone, and welcome to the second session of Digital Odontics webinar series. This is Mahmoud Al-Bashti with you today from Digital Odontics International Academy. It's our pleasure and honor to welcome our guest speaker, Associate Professor Rosemary Seelaus from the University of Illinois at Chicago, United States. Rosemary will share with us her experience in facial prosthetic rehabilitation in the digital age. Rosemary is a senior anaplastologist at the University of Illinois Health Craniofacial Center. Her clinical practice specializes primarily in the treatment and fabrication of implant-retained facial prostheses and treatment virtual surgical planning for the facial reconstruction using 3D imaging and printing. She maintains and emphasizes on the ensuring that the informed patient and family is central to the defining treatment goals and successful outcomes. She is leading in her field. Rosemary has lectured extensively worldwide on her clinical and technology expertise and has mentored graduate and postgraduate students both in the United States and abroad. Her primary research interests are central to the clinical application of 3D digital and coloring technologies to define best practices and treatment outcomes for surgical and prosthetic reconstruction and rehabilitation of the head and neck patients. She has served in multiple professional scientific and editorial boards and committees for both research and clinical activities. During this session, Rosemary will explore the various digital technologies used in facial prosthetic rehabilitation, such as 3D scanning, virtual modeling, and additive manufacturing. She will discuss their impact on the treatment planning, prosthesis design, and patient outcomes. She will give valuable insights into the benefits, challenging, and future possibilities of facial prosthetic rehabilitation in the digital age. So just before Rosemary starts her presentation, I would like to raise your attention that you can write down your questions in the Q&A session, and Rosemary will answer all these questions. So once again, let us welcome Rosie. Rosie, thank you so much for accepting our invitation to be with us today here. So without any delay, I think the stage is yours, please.
Okay, thank you, Professor Al-Bashti. It's certainly an honor to be a part of this inaugural series that has become such an important learning tool throughout the world. So I thank you for this opportunity, and hopefully my experience will be beneficial to all of you. So we'll get started.
Looks good.
Okay, great. So facial prosthetic rehabilitation in the digital age. I have been quite fortunate in that for the entirety of my 25-year career as an anaplastologist, I have worked with teams and with leaders who have supported my interest in investigation into the use of digital technologies. Probably this was before some of you were born, but we have a lot to talk about. I have a lot to share with you. And with that, I'll get started. If my slide will go. There we go. So my specialty, I am not a dentist or a doctor. I am an anaplastologist or a trained medical artist. And my specialty, while many anaplastologists make prosthetic devices for all parts of the body, I specialize solely in making facial prosthetic reconstructions and also in helping surgeons plan reconstructive surgery for the face. So I have a lot of different topics to cover this morning. First, I'll just talk a little bit about anaplastology and facial prosthetics. I'll talk a bit about the technology revolution as I have been a part of it, and I'll talk more about that later. I'll then review some of the foundations of working with technology in medical applications, what I refer to as the basics. And ironically, in 25 years, this has not changed very much. I'll give some examples of how I use technology for clinical application and show some case examples. And then also I'll talk about a topic that really has become kind of my primary passion with regards to technology that, took a new direction roughly around, I'd say 10 years ago, where we really have a responsibility and accountability to all of our patients to reduce costs and improve access to care, which has become a global initiative. And I'll talk a bit about the team I've been working with. And then simply a comment on the future. So facial prosthetics, it's well known that facial prosthetic reconstruction is a viable option for patients who are not candidates for reconstructive surgery. And up until the beginning of what we now know to be the digital age, the greatest technology advancement was truly, that which was introduced by Professor Brandemart with the concept of osseointegration and the use of implants to retain facial prosthetic devices. And we know that this has been a successful treatment option for patients who are born with different congenital conditions and who opt to not go through autologous reconstruction, as in the case of this young woman born with microtia. We also know that it's also has served well our patients who have survived trauma or who have survived different head and neck cancers. Of course, one of the challenges is that this very craft-based technique of designing and fabricating facial prostheses is very labor-intensive. Because it is so labor-intensive, it is high cost. There are limited training facilities, so to become an expert in this area, there aren't very many places to get trained or well-trained. And also, because there are limited trained individuals who are highly skilled in this, there's limited access to care. These are some gentlemen I've been working with for the past 20 years. A gentleman who's not pictured here is Professor Trevor Coward out of the UK, who just recently retired from King's College London. And he was one of the first to report on the use of digital technologies, where he used a scanning device to print a mirrored image ear for a patient being restored with a facial prosthesis. The other gentleman here, Dr. Jerry Grant in the orange, Mr. Peter Evans in the blue, and Dr. Dominic Egbeer at the ATM machine. This is in Tokyo, one of our last conferences for the ADT, Advanced Digital Technology and Head and Neck Reconstruction, when I also saw Professor El-Bashti, who gave a great lecture. But these are some of the group who pioneered the use of digital technologies and applications in maxillofacial rehabilitation. And also I want to give credit to Professor Hank Verdonk, who is no longer with us, but who was one of also a very important pioneer in using digital technologies. He was out of Maastricht in the Netherlands, and some of the very techniques that we use today, in fact, a surgical mask that I am printing right now on my printer and have been, in the past couple of weeks, is a design that he came up with. So it's important that we recognize the history and those who should be credited with really pioneering our applications. But these are some of the crew that have been working for the entirety of their careers to really identify the best ways to employ digital technologies for facial prosthetics. And here is just one of the promo slides from the last meeting in Tokyo, Japan. And I would behoove you, if this is a true interest of yours, you should look into the ADT. It's a small group. We're a small global group, but we're truly a group of individuals passionate about really pushing forward the development of digital technologies in our field. And Professor Dominic Egbeer, who works out of Cardiff, the University of Cardiff in Wales, actually did his PhD on fully digitally designing an implant retained ear prosthesis. And he is probably the one who has come the closest to truly understanding the specifications that are necessary and the ability for us to do this in a way that it can be clinically adapted. There are still problems with this in terms of precision, but technology is improving. And Professor Egbier is also someone who has become very committed to quality management in digital applications. And so he too is someone who you could look to as a mentor. So what have we learned in the past 25, actually it's been much longer, 35 and 40 years that we've been working with digital technologies, and very quickly working with, for instance, simply printing 3D anatomical models before surgery. We had many realized benefits, including improved accuracy and predictability, reduced operating time, in particular in the operating theater, reducing costs because operating time was reduced, improving treatment efficiency, improving outcomes, enhancing surgeon preparedness, and essentially this all equates to greater patient and clinician confidence in treatment. So we already know this. And what has been fortunate is that young people like yourselves who have come through dentistry or through dental technology or anaplastology, who really jumped onto the bandwagon of recognizing the potential with digital technologies, what we find is that young individuals who are technology driven become very, very creative. And this is an example of a young dentist who I mentored out of Indiana, who rebuilt this gentleman's jaw after a mandibulectomy, and using various digital techniques, he was able to come up with a fully digitally designed mold and prosthetic device that helped to restore this individual. And what's nice also about technology, one of the most common technologies that we use every day is our cell phones. And Travis here, Dr. Beliki, would call me and just say, hey, this is what I've done. And he would show me pictures and say, what do I do next? What do you recommend? How should I design this? So really, technology has enabled us to make the world a much smaller place where we can access one another, like right now. This is a perfect example. So I'm able to share my experience with you. And my experience started out working with a professor in industrial design. And I truly think industrial designers are tremendous people and incredibly creative and innovative, and the ingenuity that comes out of that particular profession is astounding. So in working with this gentleman, Professor Robert Lederer, back in the early 2002, I think is when we first began working together. I learned so much from his techniques, and we began working together very quickly and really making rapid advances in what was at the time the available applications for medicine. So you see here, Robert is designing in a reverse engineering manner, as opposed to forward engineering, which is more like the way an engineer designs a part in a CAD system. We're working with reverse engineering, where we're taking the existing human anatomy and working backwards. So here he is designing with what's called a microscribe, an implant for a cranioplasty procedure. And ultimately, I like to break down the way that we work with technology into three main components. We have the ability to acquire patient data. So in working in a reverse engineering way, we first have to capture the data from which we will then design a treatment or a prosthetic device or surgery. So here are some different examples of ways in which data can be captured: with radiographic imaging, with photographic imaging, with laser scanning, with MRI, with probe scanning, photogrammetry, computerized tomography, cone beam computerized tomography, and ultrasound. These are all different ways that we can capture data related to our patients. And then once we capture that data and we get it into a digital environment, there's no end to what we can do with it. We can forward engineer, for instance, a mold like you see on the left here, or we can plan surgery like you see in the central portion, where I'm placing implants to retain an ear prosthesis. And of course, we can print things. But also, we don't necessarily need a physical output. Some of our outputs actually go into navigation systems or simulation systems, or we look at analyses with FEA, finite element analysis, or looking at volumetric analyses, and any other kinds of simulations so we can better understand our treatments. Of course, most popular these days, it seems, is to actually print a model. So we can print a model, a prototype, a mold, a surgical guide. And what we can also do, another system that I work very much with, is a computerized color formulation system. So working with computerized spectrophotometry, I can actually measure the skin color of our patients. And there are many different types of printers, SLA, selective laser, stereolithography, SLS, selective laser sintering, EBM, electron beam melting, FDM, fused deposition modeling, MJM, multi-jet modeling, LOM, laminated object manufacturing. And some of these technologies have changed, but what's important for you to understand is to understand how these different 3D printing technologies employ different materials, how they function, what is the labor involved with cleaning up models, what is the cost for sure, and then what is the application. When you need a 3D printed model for surgery, for instance, sometimes an acrylic, soft tissue, resin model is sufficient, but other times a metal model really is needed, and that can be done with SLS or EBM. But there's costs associated with these. So obviously, you really need to do your homework and have an understanding of these different printing devices to best understand how they should be employed in clinical applications. But let's break it down. I've just described it to you. We acquire data, then we do something with the data, and then we output it in some way. And when I first started, I primarily worked with photographs, two-dimensional and three-dimensional photographs. One of the most effective technology methods I use is simply using two-dimensional digital photographs in Photoshop. And it's become one of the most effective and efficient tools I use in improving the accuracy of my prosthetic devices. Of course, there's medical CT. And when I first started, there was only medical CT. Cone beam didn't exist. So I am dating myself. And at any rate, at the time I worked with Mimics. I worked with Magix, which is an STL cleaning software. It's very sophisticated engineering software. Simplant, which some of you may know, and also Photoshop. And then at the time, we primarily used CNC milling because it was the most accessible in terms of cost for us. And then also FDM, fused deposition modeling, one of the old Stratasys machines, which was, I think it's not even on the market anymore. But these were some of the technologies that we could access back in 2002. And many of these have been around for ages. This is an important point, that use the technologies that you can access. And this is where your creativity comes in, that you know how to work with the technologies in order to serve your clinical needs. But ultimately, acquiring data, doing something with it as in design, and then outputting it in some way is really what it all breaks down to. And this has not changed in the entirety of since we've been working with these technologies. So here's some examples from our clinic. This is the engineer I work with, Dr. Linping Zhao, who's using the Vectra 3D photography system to take 3D images of my patient. Then we also have a cone beam scanner up in the top. We have another 3D MD system over in the corner. And I love 3D photography. I'll talk more about that later. And then we also, of course, more recently have the Trio scanner for intraoral scanning, but we also use this in off-market ways or off-label uses in scanning the face. And then we have our setup of computers where we can design with simple wizard-like digital design, or I work with sensible freeform, 3D Geomagics, as well as many other design softwares, ZBrush or various other things. There's many other types of softwares you can use that are actually available online and free. And then here's our 3D printing lab where my face mask is sitting this morning. And a lot of this was supported by our fundraising group called Face the Future Foundation. We also have a virtual surgery and simulation setup, and Professor Al-Bashti has actually tried this. It's a really fascinating system where 3D reconstruction with the fibula for the mandible or the maxilla can be done very, very efficiently and effectively with many different accurate measurements and designing cutting guides and things like that with a 3D party company and software. But this has become kind of the standard of the way that we work. And orthodontics also is a field that really leads the way in defining ways in which we can use technology for our patient treatment. Here is the setup for what I call my clinical color science laboratory. And this was very carefully designed. I designed this room, and I designed it, I'll show you in the next slide, very specifically based upon color science. I've been studying color together with Professor Trevor Coward for many years, for 25 years. And this is the setup where the spectrophotometer is used to measure the skin color of the patient. And using software that was written by a gentleman named Charlie Carroll out in Bath, England. He has written some software that is calibrated with the pigments and silicones that we use in facial prosthetic fabrication so that it will predict a formula for using for the base color. And here you see me working with one of my students and a patient and mixing up these colors. And here's the system close up. There are specific pigments that I purchased from Charlie. This is the spectrophotometer. This is the same device that's used in the automotive industry, in the food industry, in the paints and plastics industry. And we simply have been borrowing from manufacturing in the automotive industries and simply adapting these technologies to work in our field. And this room was designed after what's called a color harmony room in the automotive industry. So when a car is built, different parts of the car, the molding, the paint, the leather or the vinyl, all of the components within the car, they're all made and fabricated and manufactured in different countries. And then they're brought together, for instance, in Germany, for instance, or in the United States. And they put the car together and then they put it in one of these color harmony rooms. And this color harmony room, what it does is it's set up with 3 different illuminants: incandescent, daylight, and fluorescent. And you well know that lighting has an impact on the way our prosthetic devices appear as they relate to matching the human skin or matching the teeth. And what you see here is the paint that was used in this room is a scientifically perfect medium gray, which is void of color entirely. It's the equivalent of what we would call a Munsell 7 or 8. It has no finish on it. And so what it does is it not only creates an environment where I can more accurately evaluate color. This is the same paint that is used in color booths, in the printmaking industry, and every other color assessment type industry. It not only allows for me to see color more accurately, but it also allows me to calibrate my instrument of color measurement, which is the human eye, by simply looking at the paint. It helps relax and balance the cones in my eyes so that I become a more accurate human instrument of color. So how do we use all these digital technologies? Well, of course, we use them to virtually plan surgery, for both planning the placement of implants, as you see here, but also in designing the prosthesis. This was me working on a surgical plan back when we had different technologies. So it was medical CT. So there were limitations in the way that the data were captured, which is why you see that this gentleman's head is only showing half of the ear. I then digitized a plaster cast of the ear and then imported that. This is all done in Mimics. And then this is what was this mask design, this surgical mask design is actually the Hank Verdonk mask style surgical guide. So I credit Professor Hank Verdonk, who contributed so much to our field. But what's great about this type of planning is that we can use the planning and all of this work that I've done in front of the computer, both for designing for the surgery, but also, and here we see this is a metal guide. That was an early version of a metal guide that was printed by Professor Dominic Egbier. You see how small it is compared to that matchbook. And This was done with selective laser sintering. It's stainless steel. He has a much slicker design that he does now, or sorry, it was selective laser melting, my apologies. But this, what's nice about the metal is it really grabs the bone. Acrylic will slide on the surface of the bone and on the periosteum. A metal guide will really grab the tissue in the bone. So that's quite effective for accuracy of placement. But what's nice is beyond just planning for the surgery, we can use the same information and produce a prototype to come up with the design for the prosthesis. So I've used this same data to make a wax prototype that I can fit directly over. You can see the healing abutments in the photograph on the right. And I literally am just positioning this wax prototype directly on the patient's ear. And the position is pretty much right where it needs to be. We might have to make modifications in the bar design. I prefer a bar clip design for ears. But very quickly, we can save time and not having to worry about the size of the ear and the position, the AP position and the superior inferior position. So a lot of this work we can do well ahead on the computer. As far as orbital, here's an example of planning implants for orbital implants. And for orbital implants, I like to plan placing as many implants as possible. This is primarily due to the fact that the orbital bone is much less dense and has higher failure rates of implants compared to the temporal bone and the mastoid, for instance. We also have similar failure rates in the nasal region. Thankfully, now zygomatic implants are giving us better opportunities to employ, the stronger bone of the zygoma that might be out of the field of radiation for some patients. So technology continues to keep pace with us and give us greater opportunities to serve our patients in the most efficient way. And here, this was all designed by a former patient or former student of mine, where she did her own design of various designs of a bone fitting guide that were going to be printed in acrylic. They actually were printed in they were printed on a Z-Corp machine. So a Z-Corp works with cellulose and cyanoacrylate, or a glue, to fuse the different layers together on this cellulase-based print. It's easier to clean, but the finish on it is a little suspect. And because it is a cellulose and the cyanoacrylate only penetrates to a certain degree, there are challenges. It can't really be cut in the operating theater because the powder will fall out. So we don't want to create that situation in the operating theater. Additionally, in the orbit, we always plan for sleeper implants, as I do actually in most cases. And that is simply to ensure that we have implants available to us in the case of a failure. Here's the examples of the different types of designs. She did 3 different kinds of designs to see. Here is where we're working in development. We're trying to understand what's the best design to fit a surgical guide on the bone. And so we tried, there are 3 different types, two different designs where they employ 2 pieces and then a single piece. And you see all these pieces in the operating theater. They can all be sterilized and used directly by the surgeon to make measurements, to check various things. And we have the guides both 3D printed and then reproduced in a resin that actually can be placed directly on the patient. You might also see in the image on the anatomical model on the table that we've outlined where the guides go. Sometimes part of the time-consuming thing is the surgeon simply trying to figure out where does the guide fit on the patient. So giving the surgeon some way of understanding where the guide should sit is often very helpful, and a simple thing to save in time in the operating theater. We also use these technologies. This is an example of 3D photography. I love 3D photography for children. It's less invasive. It's easier to capture a good scan compared to sitting them in a cone beam where they might not actually fit. They might be too small to capture a good image. But as well, 3D photography, I said I loved it. It's one of the most efficient technologies I've ever used. You can capture a 3D photograph in a millisecond, and then by simply doing, and I'm working in free form in this example, by doing a simple offset off of the face of this child, I can create a face mask, and this is for autologous ear reconstruction and sometimes possible Baja placement. And here's the guide that I was able to print. This can be tried on the patient. It gives the surgeon a lot of information about placement of the ear and various things like that. So this would have been the contralateral ear from the patient that I then did a Boolean union with the offset of the patient's face to demonstrate to the surgeon where the ear should be placed during surgery. Prosthetically, they'll take all of these systems together and let's put them all together. So here's an example of a young boy, a 7-year-old boy, who I made an adhesive retained prosthetic ear for, and so that he could get older and make a decision about any kind of definitive treatment. So here you see him with his microtia. He needed to wear sunglasses. He wanted to wear sunglasses. Remember, ears have function of holding up glasses, of holding up safety glasses, sunglasses, eyeglasses, masks, of course, now we know that. But here's an example using cone beam technology. He didn't have implants, we're planning that now, but this image is simply of a cone beam scan. And then with that information, I could actually design on the computer using his left ear and mirroring it to the right side, superimposing it over the microtia on the right. I could then do a simple Boolean subtraction, print that ear, reproduce it in wax, and together using, I finished the wax with the patient in the clinic, then using the color technology, I was able to come up with a quick, a nice result for him, and limiting the amount of time for him in the chair. 3D photography, as I mentioned, one of the most efficient and really the technology I think that has delivered the most in terms of efficiency. In the right case, and in particular with nasal prostheses, this serves very well when you have few undercuts. So for this gentleman, using 3D photography, and here's other examples of other patients that I have used 3D photography for. So for the nose or an orbit with limited undercuts, 3D photography serves very, very well. You can quickly come up with a prototype by either using existing anatomy, so for an orbit, the contralateral orbit, or in this case, a family's donor nose. So you see the daughter standing with my patient here in the top photograph, and using one of the daughter's nose, I simply adapted it to the proportions of my patient's face. At the time, we were using milling because that's what we had in-house. I milled the prototype of the nose, reproduced it in wax, and could very quickly come up with an adhesive retained prosthesis for this gentleman just in time for his 83rd birthday. And he said in these photographs that, it had been several years that he remembered even smiling. So in this particular instance, I also liked these photographs because in a way it demonstrates the problem we have with color, which is metamerism. And I was explaining a little bit what the color room was designed for. It's designed to help us reduce the effect of metamerism. And metamerism is the effect when two different materials appear to match in color under one lighting condition, but no longer appear to match in another lighting condition. And these three photographs demonstrate different kinds of lighting, but you see the nose still appears to match the color of the face. So in this case, the color match was quite successful. It's not always the case. Here's another example of using a donor nose and fitting it to a similar case using freeform, 3D photography and freeform, using a donor nose. I believe the donor was this gentleman's son. I fitted the face or the nose onto the face. And, many of us have described worldwide the development of different digital donor nose databases or digital libraries of noses, and many have contributed to this. Interestingly, at the very first conference we had for the advanced digital technology, and this was back in 2002 in Edmonton, Alberta, where we attempted to have a small meeting of people interested in this globally. I think I gave 7 lectures at that first meeting, and we were the host, but we had such an overwhelming response, we had to turn people away. But I gave this one lecture, and it was one of, let's just say I was a less seasoned lecturer, and I was quite nervous giving this lecture, and I was giving a lecture about milling, making a nose prosthesis and milling it and things like this. And in my mind, I had already thought of this idea of creating a digital library of noses. And this gentleman asked, he says, how do you see this technology contributing to the future in facial prosthetics? And in my mind, I knew it, but I was so nervous. I did the classic, froze at the podium and kind of didn't even hear his question. So it happens to all of us, but thankfully I'm beyond that. But yes, the answer to that question was, well, we can build a digital nose library. So there's my answer to that question 25 years later. At any rate, this is, many people have described this in the literature. You see lots of it now, and it's a very, very effective way. I have lots of ideas, I think, of how this could be improved. The military has created this for all of our military personnel. Probably that anyone who is entering, unfortunately, the wars that we still have ongoing, that before they even are deployed, they get a medical CT of their head so that we can reconstruct it. So it's kind of a scary thing, but it's the reality. So lots of opportunities here. Let me know if you're interested. And, there are all different kinds of sculpting tools. One of the main things here, what you can see is, you see that I have a 3D photograph of the patient in gray, and then I have the yellow is a digital donor nose. And you see that the proportions, the tricky thing is matching the proportions of the nose onto the face. So you need to understand the canons of facial proportions in order to do this. You see that the bridge of the nose of the donor nose is more narrow than the patient's. The height is greater than the patient's face. Sometimes with surgery, the facial height is decreased and is shortened. So these are all important, but I'm in the process of kind of resizing or reproportioning this nose for this patient, fitting it onto this patient's face. For this patient, I had the fortunate opportunity to see the patient ahead of the rhinectomy. As you know, this is not always the case, but for this gentleman, I was able to capture his nose, which is quite an interesting nose. Then you see the 3D photograph after the rhinectomy. You do see the evidence of how the lip is pulled up following surgery, but you see the picture of him before and after surgery. So notice the differences in the lip, and notice the difference in the alar groove and the scars and how that skin is pulled. I think he was also irradiated. You can see evidence of that. So these are all important things to pay attention to. But I was able to, using his the nose from his pre-surgical photograph, I could fit it onto his treatment face. And then using an offset, I came up with a very, very simple design to fabricate this nose. You could see here, I printed in an elastic type of material. That's the big clear nose on the right. That's basically an offset on the outside of his nose that fit onto his face. And then just fitting this elastic mold over the treatment nose, I was able to come up with this wax prototype that I then tried on him in the clinic. And I was able to quickly come up with a nice prototype for him to finish his prosthesis, which you see here. We can combine techniques. So Digilog, a lot of people refer to Digilog, meaning a combination of digital techniques and analog techniques. So here's an example of this using 3D photography for these two gentlemen. And that on the left-hand side, so you see that he had further surgery. He started out in one situation and then had his full nose resected, and you see the bone exposed. But by using the left side of his nose and mirroring it, I could come up with proportions for his nose, and then literally just taking utility wax and with my thumbs filling in the indentation, I could come up with a reasonable representation of what his nose would have been like. Then I've reproduced it. It looks pretty, bulky and clunky in reproducing the wax, but sometimes that happens if you've ever done it. And here I am trying this on the gentleman. The other issue with this gentleman is he had a great deal of lymphedema in the face, and 3D photography became very effective in doing a digital impression. When I tried to make a conventional impression, there was so much lymphedema in the face, and the weight of the silicone caused distortion. And you may be able to see this I think in the areas on the right photograph, I think it is, you may see the gapping where the lymphedema, I couldn't capture an accurate impression, but I was able to do that with 3D photography. So this is an area where, technology helps us in ways that the analog approaches are not effective. So always think about, it's not just about replacing what we do with digital techniques. There's always an adaptation of technique, an exploration of how do we blend our techniques, analog and digital. And here's an example of this. This is that gentleman that I had planned the surgery using the Hank Verdonk mask and combining the different techniques. And so what we did was we designed this mold that was built in an elastomer, and that mold was actually built by Materialize. I forget which rep I was working with those years. I've worked with probably a dozen reps from Materialize since I began working with them back in, well, not even 2000, in like 1997, I think, or 98, I was working with Mimics. But here you see us just melting wax and pouring it into this mold that gave us this prototype that you saw earlier that we could fit directly on this patient. And you see the position is quite reasonable for this gentleman. So it took a little bit of finishing, obviously fitting the bar in there and fitting the substructure, all requires adapting the shape of the ear. But getting to this point gets us well ahead of the game in designing facial prostheses. I mentioned before that it's essential that you understand the differences of 3D printing technologies and that you understand the different types of printers, the different types of materials they produce and the cost, and what is most appropriate for your clinical applications. That is also true of the data you work with. You must understand the data because remember, garbage in is garbage out. And anything, you need to understand, when do you need a medical grade CT? You should very easily see the difference between this medical CT and this cone beam CT. And if you can't see it, then you need to study it. So in these circumstances, for certain surgical procedures where greater precision is needed, most likely a medical CT is needed. So for some orthognathic type procedures, for any kind of middle ear surgery, for anything where true precision is needed, you need the data of a medical CT because a cone beam CT is 10% the amount of radiation compared to a medical CT. And that's why you see the difference in these two images. For cone beam CT, for our applications, what we do in our clinic is typically sufficient for what we need to do, but we're not doing anything of tremendous precision. So usually cone beam CT is sufficient, and that's what we use and have one in our clinic. It also contributes to efficiency because we can just get our technician to take an image on that same day. And that's what we begin doing is we capture all records in a single visit, 2D photographs, 3D photographs, cone beam CT, trio scan, color measurement, every kind of measurement you might need that is digital, capturing all of that ahead of time so we can then plan the treatment in an appropriate way. But having all these systems is expensive. And this is an approximation of the systems. Now we have more systems since I figured this amount, but it's expensive and not everyone can acquire all of this. So of course, necessity is the mother of invention. And this is a well-known adage. And so I have had the great fortune of working together with a group from Brazil. I mentored this young dentist, Dr. Rodrigo Salazar, in the center of this photograph, who was under the supervision of Professor Luciano Dib, who is an oral maxillofacial surgeon in Sao Paulo. Rodrigo Salazar is from Peru. I first met him at a conference in Argentina when I was lecturing very much on the same things I'm showing you now, but talking about 3D photography and demonstrating efficiency with 3D photography. It happened that Professor Salazar was a photographer. He was a student of photography and loved it, took all the photographs for the conference. And he came up to me afterward. He said, I want to work with you. And we've been working together ever since. It's been 10 plus years, I think, since then. And so what he has done, and I have supervised him both for his master's and his PhD together with Professor Dibb. And what he did is essentially he wanted to replicate what I had in Chicago using a mobile phone and free applications. And so we did this, and this was our first paper, monoscopic photogrammetry to obtain 3D models by a mobile device, a method for making facial prostheses. And so what he did was that, he was able to, using a very, very simple technique of capturing 3D photography by means of serial single images at 3 different elevations. And there are now better protocols. We've come to realize that more photographs are needed in order to get a good representation of the 3D anatomy. And it turns out that the phone I have, a Samsung Galaxy Note 10, is actually one of the best cameras for capturing this. And essentially, the more photographs, the better. So if you can get 70 on one elevation, 70 on another, and 70 on the other one, you're going to get the best representation. And this is some of the newest things. We're still developing this particular technique, but with this technique, we've been able to treat so many patients. Brazil shares the same problem that so many other countries do in the world, in that patients in remote areas are not able to access appropriate care. And so using 3D printing technologies and using color printing, we're trying to understand, can we truly print color with a 3D printer that replicates the colors we use in facial prosthetics? That's a research project I'm working on right now that I've got a grant for. So if you're interested in that, let me know. I need some help. We're also interested in, can we use the mobile phone to measure color? And there are ways in which this has been demonstrated. This is a poster that I presented at another ADD conference in Amiens, France, and using the smartphone camera to come up with a way of measuring color. And people have looked into this, and there are other simpler devices that look at measuring color. And this is done. You can find this all over in industry. In the paint industry, there are all kinds of apps where you can measure the paint on your wall in your home to pick the right paint. There are also apps like this for dentistry. You've probably seen some for measuring tooth color, various things like that. So it all exists. It's just a matter of our identifying what is going to be the best and most suitable for our applications. Again, we see blending technologies, 3D scanning with the Trio scanner, which also measures color. I've not tested this yet, but I do want to test this and see how it calibrates with spectrophotometry in my system. But the reality is, as I mentioned before, the number one technology that we all access on a day-to-day basis is the smartphone. And now there are 3D printers. This is a 3D printer that you attach to your phone and print it directly from your 3D phone. Or you can build, and this is only $100 US. Look at the difference. Look at the difference there. So you can also build your own 3D printer. I know Professor Al-Bashti has already seen me present on some of these concepts, but this is exciting stuff. So if you're this kind of person, if you like to build things and figure things out, then do this. And that's a good way for you to get started with technology if you don't have access to it. So is it feasible? Can we really do this for our patients? Because we have a responsibility, and we have a responsibility to make decisions about what technologies to use, all driven by our patients' needs and what is the best and most efficient and lowest cost solution for their treatment. So they are our motivation. Don't forget this. Don't make the mistake. It's normal to make this mistake. I call it magpie syndrome, where you're attracted to shiny objects. I was for the first part of my career. And then it was unfortunately, a patient dying that was the wake-up call for me to say, all right, we have to toe the line We need to be accountable to our patients and make the decisions of what technologies are appropriate for them, and to use technology so that it serves us, not just use technology for technology's sake. In all of this time, this has remained the same. Acquisition of data, manipulation of data, and output of data remains the same. None of this has changed. We're just about to print a book chapter in a new book on 3D printing in medicine. And in the chapter that I wrote together with Dr. Jerry Grant, I use this diagram. It hasn't changed. And many people have described it in the literature, but this has not changed. So keep in mind, we must not constrain ourselves to our current traditional methodologies, technologies, and ideologies. So take a chance, step out on the glass platform. This is the Sears Tower in Chicago. And that was the words of my good friend and colleague, Professor Trevor Coward out of London. So take a chance, become creative. You're the generation that's really going to define what and how we are going to move forward for our patients. Thank you. Please feel free to reach out to me. I don't do a whole lot on social media, so you're best to reach me by Gmail or WhatsApp. So I thank you for this opportunity. I hope that you have enjoyed this lecture and found something to take home with you. And Professor El-Bashty, I turn it back to you.
Thank you so much, Rosie. It was amazing as usual. You really introduced us to the inspiring technologies, starting with the more sophisticated technologies back in the history, 25 or more years of experience you shared with us. And I like the way you presented the webinar, because you introduced everything in systematic way. And I think everyone is like it because they got a great message. And when you say, try to use what you have and be creative and work on that, that's a great message, because nowadays, many of the practitioners, they don't have the access to the expensive technologies, but they have to think about different ways. And with the mobile applications, it's another direction for us. And you give a clear message to the audience and the professionals in the future that they want to get the digital technology. Try to use a simple way of technologies, then you can be a creative and build your own system based on that. So thank you so much, Rosie, for that. And audience, if you have any questions, please don't hesitate to write your questions here. It's a great chance that Rosie with us today, she can give you the answer. She is the expertise in the field. Rosie, with the mobile technology, sometimes it's very difficult, especially for the Z-axis, to get undercut area. So do you have any idea how to overcome this issue based on the research that you have done with the other colleagues?
So one thing is, and this is from when I was in Brazil last fall, I try to get to Brazil to work directly with the team. And, we're even testing our methodologies by, I'm actually trying to treat a patient in Canada using the system in Brazil to test it out. So that's kind of our viability, I suppose, test. But one thing is for sure that capturing more of the photographs. So I think it was like at least 72 or as many as you can get. Like even I guess holding your hand on the phone and doing those kinds of capture at those 3 different levels, that would be one thing. The other thing would be to look at the possibility of combining technology. So for instance, if you took that surface data from the model with the mobile phone, and let's say you had access to like a Trio scanner, for instance, or even if you had access to like an older scan of a CT, let's say it was a CT, but it was done in more slices. You know, sometimes the older CTs have gaps because they're done at 5 millimeter distances, that you might be able to blend those together, create a 3D model of whatever you get. It'll be stair-stepped, but and then if you were able to combine the surface data from the mobile phone or from the Trio scan, you could, you know, blend those two data sets together. That might be a way. You may have to, what I often do, if I truly need to capture, let's say we have a rhinectomy, and if you truly need to capture the undercuts there or in the orbit, that what I'll do is I'll come up with a prototype. I'll print a prototype, and then I'll use that as a custom tray. And then you can do like a modified impression. So you can maybe go direct to a definitive impression rather than doing a preliminary and then a definitive impression. So you're already creating improved efficiency and improved experience for the patient because you're taking a step out. So those are some ways I might look at doing that.
Yeah, there you go. And the other thing that, you know, that the technology is rapidly, you know, advancing and pushing us to follow up with all these, you know, developments. And nowadays, artificial intelligence is a very important topic that can benefit our field and our patients and our practitioners as well. So have you started any kind of artificial intelligence with the data that you have? I know you have very large size data regarding facial prosthesis. Have you tried that way?
So we're working on that. We're working on that. And that's a bad word these days, right? Artificial intelligence. So I'm scared of it too. But in terms of the process of designing the prosthesis, we want to write in artificial intelligence into that. So it becomes much more of a turnkey solution. So I know that the team on the ground in Sao Paulo is working on that and looking at, you know, we're looking at ways of where do we want the AI? Where do we want to employ it? Where does it make the most sense? Obviously, there's a lot of places where in coming up with the design prototype, or, you know, there's a lot of opportunities to write in AI. That said, I'm going to describe to you a problem that I'm sure you're well familiar with. The problem is the demand of increasing patient volumes is limiting the amount of time for R&D. So this is my reality every single day. You know, I have lots of research projects that are sitting on the shelf because I am overwhelmed with being too busy. I have too many patients to treat right now. And that's just in Chicago and my surrounding states. So in Brazil, it's a real problem. And the other thing that we're looking at, and the foundation, it's Mas Identidade is the name of the institute. So, and Mas Identidade means, you know, bringing back your identity. And, you know, this was really the dream and passion of Dr. Luciano Dib. But right now they're actually working on the whole operational processes. So because this is a real challenge, and that the reality of increased patient volumes, and it's a small clinic, they have 2 chairs, you know, the photography room doubles as the color room. They've mimicked my color design. You know, it's a lovely setup, but it's a small setup. And being able to meet the patient volumes that are going to come out of this in Brazil is, you know, that's the biggest, I think, challenge coming down the pike. So we want to keep pushing and pushing and pushing, but you need money and people and, you know, hands on deck, as it were.
Yeah, it's totally understandable. I know it's, you know, this is a huge work. Yes, really needs a lot of money and people working on that. But when I asked you about artificial intelligence, because when you work smarter, you will get efficiency, work efficiency, and you can work with a lot of patients in a shorter time. But again, I mean, the concern of ethics and other issues is still exists, you know, and everyone now is still afraid to engage in the artificial.
Yeah.
Yeah. So
Yeah, it's a big problem. There's going to
yeah.
be a log jam somewhere.
Yeah, exactly.
Yeah.
But hopefully, with the hard work, we can find a way to make our work more efficient, to reach much more patients who are in need for the facial prosthesis. So I really thank you. It was very nice time with you, sharing your experience. It's very intensive experience. I really like it, the way you presented. So thank you so much. As a tradition for digital odontics, I would like to thank you so much, and I would like to present a certificate of appreciation. So we hereby express our sincere appreciation to Rosemary Seelaus in recognition of her contribution as a live webinar speaker for the Digital Odontics webinar series on the topic of facial prosthetic rehabilitation in the digital age, that was presented on Tuesday, July 25th, 2023. Rosie, thank you so much. I highly appreciate it.
Thank you, Mohammed. Thank you so much. It's been an honor.
Thank you, everyone, for your time, and be tuned. We have still some webinars in the coming weeks, so don't hesitate to come back to Digital Odontics and watch the other webinars. Everyone, have a nice morning, nice afternoon, a nice evening. Bye-bye. Bye, Rosie. Thank you.
Bye-bye. Thank you.